Hi students, in this video I'm going to show you how to do a chi-square goodness of fit test. I'm going to show you how to do hand calculations, and I'm also going to show you what this would look like with SPSS output. My name is Dr. Marie Wong. So for the goodness of fit test, this is where we have a situation where we have frequencies across different categories. So in a goodness of fit test, the null hypothesis is simply that there are equal proportions across categories. The research hypothesis is that that's not the case, that there are unequal proportions across categories. I'll show you an example in just a second. But before I do that, I want to just talk to you quickly about the critical value. For this particular test, I know I haven't shown you any data yet, but for the test that we're about to do, we're going to set alpha at 0.05. Our degrees of freedom are going to be the number of categories we have minus 1. In our example, we're going to have 3 categories. So our degrees of freedom are going to be 3 minus 1, which is going to be 2. So we would look this up in a chi-square table. You can find chi-square tables at the back of statistics books, or you can look online for them. And in a chi-square table, you need to know your alpha level and you need to know your degrees of freedom. And if you looked up degrees of freedom of 2 when alpha is at 0.05, you'd get a critical value of 5.99. So in order for us to reject our null hypotheses, we would need to get a chi-square test that's bigger than 5.99. And if we did that, if we got an observed chi-square that's bigger than our critical value of 5.99, we could reject our null hypotheses, and then we would say that there are actually unequal proportions across our categories. One thing that's nice about chi-squared, you should never get a negative value. So we don't have to worry about having 2 tail tests versus 1 tail test. We simply are we only have to be concerned with positive numbers here. So if you get a negative number for chi-squared, something's gone wrong in your calculations. So what I want to show you, I'm going to use a simple example, and in this example, this is based on the Neapolitan ice cream. So if you've ever bought Neapolitan ice cream at the store, it has 3 flavors, right? It has chocolate, it has vanilla, it has strawberry. So we could ask people in the general population, what is your favorite ice cream flavor? And so maybe I go out and I find 100 people, my sample size here happens to be 100, and I say, what's your favorite flavor of ice cream? Half of them say chocolate, 30 of them say vanilla, and 20 of them say strawberry. So my observed values or observed frequencies, this is what people told me when I polled them and said, what's your favorite flavor of ice cream, chocolate, vanilla, or strawberry? 50 said chocolate again, 30 said vanilla, 20 said strawberry. So these are frequencies or counts. Remember my null hypotheses. My null hypothesis is stating that we expect there to be no difference in these categories. We expect equal values, equal frequencies across these categories. So the way that I have to fill in my expected values. And those expected values, I fill those in based on my null hypotheses. Again, the null is saying there's no difference, that people prefer equally chocolate, vanilla, and strawberry ice cream. If that were the case, what I would do is I would split my sample size of 100 equally among those 3 categories, right? So to get my expected frequency, if you look in the top right section of the slide, you'll see that expected frequency is, we represent it as F with the little e by it, is P times N. N is just my sample size. P would be the probability of landing in each of those categories. And the probability is just going to be simply based on the number of categories that I have. So if I have 3 categories, my probability is going to be 1/3 or 0.33. If I have 2 categories, my probability would be 0.50 or 1/2, and so on. In this particular case, I have 3 categories, so I'm simply taking 100, I'm dividing it by 3 because I have 3 categories, and that's where that 33.3 is coming from. Okay, so there again, just to sort of, I know this can get a little confusing with chi-square. In order to do a chi-square calculation, we have observed values. Those are the ones that are given to us through polling, or we have this information in our data. So the observed values are from our data. The expected values, those are ones we calculate based on the null hypotheses. In this case, the null is simply stating there's no preference among ice cream flavor, that people should fall equally in those categories. So I simply took my sample size, which was 100, divided by 3 since I have 3 categories, and that's where those expected values or expected frequencies came from. Okay, so hopefully that's clear. So what we can do next after we've set this up, so in order to do the hand calculations, you have to know what the observed values are and what the expected values are, okay? And certainly ice cream manufacturers, when they manufacture Neapolitan ice cream, are assuming equal preference, right? They give you equal amounts of chocolate, vanilla, and strawberry, when in fact, that's not always the case in terms of people's preferences. So that completely explains why, if you ever buy Neapolitan ice cream, why there's always just like one kind of ice cream left. At least that's what happens in my family anyway. All right, so here's the formula for chi-square. It's actually a simple formula. It looks a little bit like there's a lot going on, but it's really simple to calculate. Remember what sigma means. It means we're going to sum up. So for what we're going to do, we're going to sum for each category. So I'm going to take each of my categories, and I'm going to take the observed frequency minus the expected frequency. I square those, and then I divide by the expected frequency. I do that for each category, and then I just sum those numbers that I get, and that's going to give me my chi-square. I'll show you an example. We'll do a calculation by hand so you can see how this works. But again, this is the formula here for chi-square. So for our calculations here, if you remember our formula, I'm just going to repeat the formula here. I'm going to write it here just so you have it handy. Chi-square, it's sigma, the frequency of the observed minus the frequency of expected values, squared divided by the frequency of the expected values. Okay, so what we're going to do is we're going to do this for each of our categories. We have 3 categories, right? So what this is going to look like here. For my first category, chocolate, 50 people had said chocolate was their favorite flavor. Remember, the expected frequency is 33, so 50 minus 33.3 squared divided by 33.3. And then we have to do this not just for chocolate, but also for the other flavors too. So for my next flavor, 30 minus 33.3 in parentheses squared divided by 33.3. And then finally, the last flavor, 20 minus 33.3 in parentheses squared divided by 33.3. Okay, so those are my that's me plugging everything into the chi-square formula. And again, you can see the 50, the 30, and the 20. Those are my observed values. I got that from my data set. The 33.3, those are my expected values, my expected frequencies. So now I just have to do my math. So if I take 50 minus 33.3 in parentheses, I do my subtraction, I square it, I divide by 33.3, I get 8.38 here. Okay. If I do the same thing, if I do my calculations for this second flavor, 0.33 is what I get there. And then for my third flavor, 5.31. All right, so now I just have to get my chi-square. Remember, I have a sigma here, so I have to add these up. So 8.38 plus 0.33 plus 5.31, that's going to give me a chi-square of 14.02. Okay, so that's pretty easy to calculate. My chi-square of 14.02, that's my statistic. That's what we calculated here. And then remember, I'm going to do a kind of a quick ugly picture of the chi-square distribution. So maybe it looks something like this. Remember our critical value. It's 5.99. So anything more extreme, anything in this tail area, is where we're going to reject our null hypotheses. And so our chi-square is way out here, 14.02. So this is our chi-square observed. So we're going to reject the null. Okay, so what this means is our results are not due to chance. What we're saying is that there's a real difference between people's preference for ice cream flavors, that these categories vary. It's not distributed equally across these different categories. So I've just shown you how to do hand calculations. I also want to show you what the SPSS output would look like here. So for the SPSS output, again, we're going to use the exact same data we used in our hand calculations. What you can see in SPSS, if I do the chi-square, it's showing you that you can see the category of ice creams occurring with equal probabilities. That's my null hypotheses. If we did reject the null hypotheses, that was our decision there. And you can see the significance level is 0.001. That's less than 0.05. That tells us we can reject our null hypotheses. If you look at the table further down where it says one sample chi-square test summary, that's where you can see my total sample size is 100. You can see the test statistic that was calculated is 14.000. That's very close to ours, which was 14.02. Again, the difference was just rounding error. You can also see we have 2 degrees of freedom, which we had determined earlier, and that it's 0.001. All right, so this would be the sort of output you would get with chi-square. And this is just showing you, sometimes in the output, you also will get a table, and this is just showing you the frequency. So remember, these are our observed frequencies. These are the counts that we got. And I put this slide in here because I wanted to just emphasize to you with chi-square, we're using frequencies or counts in our data. So if you have data that's frequencies or counts, chi-square is often a very good statistic. It's what we call a non-parametric statistic, meaning we don't have to make a lot of assumptions about what the population looks like. There are very few assumptions with chi-square, so it can be a very effective, very flexible test to use. So that's the end of the lecture. This was a quick one. I just wanted to show you how to do a simple chi-square goodness of fit test. And the goodness of fit test, it's a test we use if we simply have a set of categories and we have basically one variable and it has these different categories, and we want to know if people are distributed evenly across those categories, or if some categories are preferred over other categories, if some categories are higher frequency compared to other categories. Thank you.